Hello and welcome to the lectures on state space approach to control system analysis and design. This lecture is again on linear observers, and in this the topic of discussion is reduced order observer. In the previous one we discussed the full order observer. So while discussing the full order observer, we saw that a full order observer is of order n, which is same as the system order. Now, in systems in which the number of outputs is comparatively much smaller, number of outputs P is much less compared to the order of the system, the number of states. There, the need of a full order observer is justified. However, in systems in which the number of states not accessible for measurement, that means n minus p. N is the total number of states, p is the number of outputs, independent outputs, meaning that up to p states we have accessibility. So this difference n minus p, if it is small compared to n, if this is much less compared to the order of the system, then the design of full order observer is not justified, it is highly uneconomical. Of course, when we say this, we have in mind that implementation of observer is based upon some kind of analog circuits and components thereupon. Otherwise, these may not be valid in today's parlance if the implementation is on some kind of a hardware which will essentially remain the same for this as well as for this. But still, from the viewpoint of computations involved, not only the necessary hardware resource, from the viewpoint of computations involved, a full order observer is still computationally uneconomical if number of states which are not accessible for measurement is comparatively much smaller than the order of the system. In such a situation, we go for what is called as a reduced order observer, and it is designed only to estimate those n minus p state variables which are not accessible. And the topic of discussion, as I said in the beginning, now is the reduced order observer. Let us proceed ahead and see. We have the same system, x dot equal to ax plus bu, system of order n. Number of outputs is p, and the inputs of course is m. We have this system. As before, we considered this in case of full order observer also. However, at the very beginning, at the outset, we are assuming that the system dynamics is available in this form, in which the state vector x is supposed to be grouped into a smaller set of state x1, a smaller set of state variables x1, and another smaller set of state variables x2. Both x1 and x2 are a smaller sets of state variables than x. Together they make x. So x1 is of order n1 and x2 is of order n2. And as I said, both n1 and n2, they are less than n. However, they will add up to make n. So we assume that initial dynamics is such that these state equations can be shown in this manner, where the dynamics is available in this decomposed form, First one is here. Now it's not very clear what we want from the state equation, but it should be clear from the output equation. In this form, what we see that the output is C1 x1, C1 times x1 and 0 times x2, C1 x1 plus C2 x2. So at the outset, and this C2 is equal to 0. So at the outset we have assumed that the system dynamics is available in this form, that the output is dependent on only x1 group of states, state variables, the state x1, and it doesn't depend on x2. And the state equation is correspondingly shown in this partition form like this. So x1 dot is a11 x1 plus a12 x2 like this, a11 x1 plus a12 x2 plus b1 and similarly x2 dot a21 x1 plus a22 x2 plus b2. It is available in this form, this specific form. And of course, as I said, n1 plus n2 is n. n1 is equal to p, the number of output variables. Now, because it is available in this form, it is very clear that we can make use of that property to design the reduced order observer. That is basically the intent. So we start with the equation for full order observer. If we think of a full order observer for that system, it will be like this. Z dot is Az plus Bu plus G y minus, this should be Cz, y minus Cz. And because the states X is partitioned into x1 and x2, so similarly we assume that the observer state Z is partitioned into Z1, Z2. Z is Z1, Z2, and Z1 is of order n1, Z2 is of dimension n2. So similar to that, exactly corresponding to states x1 and x2. So that means that this gets represented in this form. Z1 dot becomes A11 Z1 plus A12 Z2 plus B1U plus G1 Y minus, this CZ is C1 Z plus 0 times Z2. So that C1 Z1 comes here. And similarly Z2 dot A21 Z1 plus A22 Z2 plus B2U plus G2 Y minus C1 Z1. Now we make use of that output equation where the outputs depended only on the states x1. So using that y equal to c1 x1, we can write x1 as this, c1 inverse y, and then it is a matter of straightforward calculation. No dynamic system is required. So the observer states Z1, they will be exactly equal to x1, which will be equal to c1 inverse y. There is no need of any dynamical system for observation of Z1. We need only to design an observer only for the state Z2, which is of order n2 and which is of n minus p dimension. So we concentrate on that equation for Z2. This becomes Z2 dot is A21, this Z1 is now x1, like from here. So A21 x1 plus A22 Z2 as it is, plus B2U as it is plus G2 into Y minus C1Z. So G2 into Y minus C1, and this Z1 is C1 inverse Y. So that comes here. So that C1 Z1 becomes C1 C1 inverse Y. And that means C1 C1 inverse is identity. So this becomes Y minus Y or 0. So this term disappears and only remaining three terms remain. So the dynamical equation for the second subset, that Z2, becomes A22Z2 plus A21 C1 inverse Y. From here X1 is C1 inverse Y plus B2. This is the equation, and in this, suppose as a very special situation, suppose A22 is a stable system, then what will happen? This system will be stable with A21 C1 inverse as the input matrix corresponding to the measurement vector Y, and B2 the input matrix corresponding to the input to the system U. So the Z2 dot will be the observer in which this Y will come and this U will come from the system, and this will be processed through this A21 C1 inverse Y, and this will be processed through B2. This will be processed through B2, and this will be processed through A21 C1 inverse. So that is how the output of the actual system and input to the actual system, they are both the inputs to this observer of the radio starter. Now this one can be accepted as it is if this A22 possesses the stability property, if its eigenvalues they are in the left half S plane, and if they are at the desired locations, then we do not need to do anything further. But that will happen only in very rare scenarios. First of all, in a general situation, A22 is not expected to be stable. Its eigenvalues are not expected to be in the open left half S plane. They can be, some of them may be in the region of stability. However, even if it represents a stable system, the eigenvalues may not be at very nice locations to yield a desired response characteristics, good response characteristics. So, first of all, A22 may not represent a stable system, and in some very few situations when it does represent a stable system, its response characteristics may not be very favorable, very desirable. So we need to design a proper observer. More general system needs to be designed for estimation of states Z2. This system need not be accepted as it is, even though A22 has stability properties. We are going to consider that, and that is the reduced order observer. So reduced order observer, like a full order observer, is also a dynamical system, and we assume its dynamics of this form. Xi is the state which is of the size same as Z2. So Xi is of size N2, And we assume that it is characterized by this equation, xi dot is d xi plus ey plus fu. D being the system matrix, E being the input matrix corresponding to the output, and F being the input matrix corresponding to the input of the system. Y and U both are inputs as far as the observer is considered. And the estimated state vector Z2 is supposed to be composed of a weighted y through L and the xi. So Z2 is assumed to be Ly plus xi. Xi is state of this dynamical system, and Ly is L times y, the output of the system. Of course, L, D, E, F all are unknown. However, we are assuming that the dynamics of the reduced order observer will apply this form. And so subsequently, of course, we will know these matrices. Again, because the main consideration involved in design of Leuenberger observer is the error in estimation of states. Now here the error is denoted by epsilon, var epsilon. Epsilon is x2 minus z2. We are estimating the states z2, and deviation from x2, the actual state, is the error epsilon, and this has to be made zero asymptotically. So we differentiate it, and by differentiating we get x2 dot minus z2 dot. Now x2 dot, please recall a little while back, it was denoted by a21 x1 plus a22 x2 plus b2 times u. So that we substitute in place of x2 dot, and z2 is ly plus xi, so z2 dot will be ly dot plus xi dot. Z2 dot will be ly dot plus xi dot. This follows from here. So we substitute that in place of z2 dot, we substitute this, which is here. So the dynamics of the deviation of observer state from the actual system state is governed by this equation, and this simplifies to this one. This part is as it is. However, because y is c1 x1, so it becomes L c1 x1 dot, y dot becomes c1 x1 dot, and this xi dot is as it is here. Now further it simplifies to this one. So this part is this one, and in place of x1 dot we substitute a11 x1 plus a12 x2 plus b1 u, and it was multiplying by LC1, so that LC1 x1 dot is LC1 multiplying to this, and xi dot, this xi dot comes from here, d xi plus ey plus fu, that we substitute for xi dot. And now we collect the terms. Okay, before that we open this and we rewrite this one like this. Now we collect the terms in same variables together. So like in x1 we have this one, we have this one, we have this one. So these three we take together. Similarly in x2 we have this one, we have this one, we take them together. In u, the input u, we have this term, then we have this one, and we have one for f. So we take them together and we write here. And this z2 is because the error epsilon is x2 minus z2. So Z2 will be x2 minus epsilon, that we substitute here. dz2 is d into x2 minus epsilon, and dly is dl, y is c1 x1. So that substitution is done. So this equation becomes like this. And then we further collect the terms together, simplify. So we get xi dot as this whole thing multiplying to x1, this whole thing multiplying to x2, this multiplying to u, and a term d times xi. Now very similar to what we considered for full order observer. If this deviation, this error, state estimation error has to become zero asymptotically, then all this term should vanish, this term should vanish, this term should vanish, and this remaining xi dot equal to d xi, this autonomous system, should be asymptotically stable system. So then the error epsilon dot will go to zero asymptotically. So that means we have these conditions for the error to become zero asymptotically. First one is this should become zero. Second one this should become zero. Third one is this should become zero. And then eigenvalues of d should have negative real parts. They should be in the open left half S-plane. So these four conditions must hold good in order that state estimation error in case of reduced order observer also becomes asymptotically zero. Now we can rearrange the terms and look at them. So what we get, the last one we had written, that if we rearrange, we get the matrix D equal to A22 minus L C1 A12. In the reduced order observer equation, we have to determine D, E and F. So D comes from this equation as D equal to A22 minus LC1 A12. It is written here, and it should have the eigenvalues in the left half S-plane. So that is this condition. Then other two, they yield this. This one gives equation for F equal to B2 minus LC1 B1. It is written here. And similarly, the first one has to be solved for E, and that gives this equation. So we get all the three equations: equation for D, equation for E, and equation for F. And in all these, still L is unknown. L is not known. So L will come when we use this property. So we have to determine an L in this D such that this condition is satisfied. And this is similar to a pole placement design. Let us see with all the equations together. This one, that the reduced order observer is a dynamical system governed by this equation in which D, E and F, they are to be found out. So based on the derivations, we found out that E will be this much, F will be this much, and D will come from this equation with the consideration that L has to be obtained such that D has poles in the left half S-plane at the desired equation. And once we have obtained L, then this E and F are fully known. And the estimate of the state x2 will be z2 given by this one, Ly plus J. So that is all the reduced order observer is. Now we concentrate on this equation. If we look at D transpose, it is A22 transpose minus A12 transpose C1 transpose L. L is the gain, So it is very similar to what we did in case of pole placement, AC equal to A minus BK. So if we consider A22 transpose in place of A12 C1 transpose in place of B, then we chose a closed loop matrix AC and we got K. Here we have to choose a closed loop matrix D and we will get L. So we will get the observer. Now this diagram shows this reduced order observer through the state diagram. So this is the system. This is familiar to us. Now what we have done, we have picked up the Y, the output of the system, and E into Y is entering on adder, this adder. There F into U is entering as well as D into that Xi enters. Now D Xi plus EY plus FU, that total makes Xi dot, which integrated gives Xi, and Xi plus L times Y, this is Y, so Y comes here, L times Y plus this Xi gives the observed value of state or the estimate of state x2, which is z2. So the entire state vector will become z1, which is same as x1, and this z2. So this z, which is estimate of x, it will be obtained by arranging z1 here and z2 determined from here. This we get. We consider one example, this third order system, x dot given by this. Now we see that here this is C1 and this is C2. So it is available in that form, the dynamics is available in that form, and we partition this. So this becomes A11, this becomes A12, this becomes A21, this becomes A22, and this is B2, which is 0, of course, this is B1. C2 has to be 0, B2 in this case is incidentally 0. So for this system, we have to design a reduced order observer only to estimate the states x2 and x3, because x1 comes directly as y, c1 inverse y, and because c1 is 1, so x1 becomes straight away y, and x2, x3 are to be estimated. So observer is required only for the two state variables x2 and x3. So we consider the design of the reduced order observer for this. As I indicated, that A matrix is partitioned to obtain A11, A12, A21, A22, B1, B2, and C1, C2. It is done. Now at this point we could use any of the formulae, but let us directly try to compute L by setting up this equation. So this is L. We have two elements in L, L1 and L2. This is C1 and this is A12, and this is A22. So when we calculate these things, we get D as this, D equal to this. Now we assume, because for the design of gain through pole placement, we have to select a characteristic equation. So we assume that the characteristic equation of PD will be characteristic equation of the matrix D, closed loop observer system matrix D. We want to place the observer poles at minus 0.3 and minus 0.4. That means this will be the characteristic polynomial. We want to have the matrix D with this characteristic polynomial. We have to obtain the gains L1 and L2 in such a way. So what we are doing, that D was this, so we obtain Si minus D and its determinant, so that gives this. And now what we do, we equate term by term the coefficients of S and constant one to the coefficients in the desired characteristic polynomial. So we have these two equations. And by solving this, we get L1, L2 as 6 and minus 1 respectively. That is, L becomes 6 minus 1 transpose. This is the L matrix, the gain matrix for the reduced observer. And once we got L, then we get D like this. We can evaluate E using that expression. It comes like this. So this is A21, this is L, this is C1, this is A11, D, L, C1, this is D again, this is L, and this is C1. And this is C1 inverse. So when we evaluate, it comes as 35 and minus 1.4. Can be checked, verified by you. And F, which is B2 minus L, C1, B1, B2 is this, L is this, C1 is this, B1 is this. It gives this one, minus 6, 1. This is F. So we got L, we got D, we got E, we got F, and that means we got all the various matrices in the reduced order observer equation. Now we are going to see how the observer response is. So we select the equilibrium of the system as the initial condition. The system was, let us go a few slides back. I'm sorry, it is many slides back. So this is the system. And the equilibrium of this system is obtained when U is 0 and X dot is 0. So what we get? This times X0 equal to 0. And you can see that X10 we have to assume, we assume it as 1. X20 will be 2 times X10 divided by 0.1, and X30 will be 4 times X10 divided by 0.2. So if X10 is assumed as 1, this becomes 2 by 0.1 or 20, and this becomes 4 by 0.2 or again 20. So the system will be at equilibrium if the input U is 0 and the state is 1, 20, 20. So we assume that equilibrium. Let us go back, go forth where we were. We came back. Here. So we assume the system to be at the equilibrium, and we assume that state equation for the observer is I dot is d xi plus ey plus fu. So we assume that xi is 0, the initial condition for this dynamic equation, as 5, 5. And correspondingly the z0, because z1 is same as x1, so z0 is same as x10, z10, z20 and z30, they are evaluated from this one, so ly plus xi Xi 0 is 5, 5. L we evaluated 6 and 1, minus 6 and minus 1, I think. 6 and minus 1. L is 6 and minus 1. So L into Y0 is 1. So minus 6. And Xi 0 is 5. So that gives 11. And 5 and 4, that gives 1. 5 and 1, that gives 4. So we are assuming that system is at equilibrium, but observer is not at equilibrium. Its states are not at the equilibrium, and that means when we simulate the observer equation, we will find that it undergoes transient, even with input u equal to 0. So that is what we are going to see. These are the x1 and z1. Because the system is at equilibrium, x1 is rock steady at its initial value 1, and because z1 is directly computed as x1, so z1 is also all the time 1. It doesn't undergo any transient. However, z2 undergoes a transient because x2 is rock steady, but z2 initial condition is different. It is 11, it should have been 20. So it achieves the value of 20 after some time. Asymptotically, it approaches the value of 20. We see from the simulations. We also see the behavior of the Z3. It also approaches the asymptotic value of 20, however, with initial transient. And this time for this initial transient here or here, this is purely dependent on the pole locations we choose for the observer. The poles far to the left from the origin will yield a faster response. However, the poles we have selected that gives this response, they take about 25 seconds for the system to asymptotically match to the states of the system, or that estimation error xi for state x2 and for state x3 becomes 0 in larger than 20 seconds, maybe somewhere around 25 seconds. For this design, so any other design could be possible. That was the simulation with input 0, system at equilibrium, and the observer states deviating from the equilibrium. Now we are doing another simulation. Same initial condition, the system is at equilibrium. However, the states xi and correspondingly the z, they are not at equilibrium. They are away from equilibrium, deviating from equilibrium. And what we do, we are also subjecting the system to input variation. So this input is 0 up to 10 seconds. Between 0 and 10 seconds it is 0. Also after 30 seconds it is 0. From 10 to 20 seconds it goes to 1 in a ramp fashion, and from 20 to 30 seconds it reduces in ramp fashion and goes to 0. So if you plot u, then let me show here. If we plot ut versus time, that waveform, for the 10 seconds it is 0. After 30 seconds it is 0. This is 10, this is 20, this is 30. It is 0. However, from 10 to 20 it rises up to 1. This value is 1. and from 20 to 30 it falls to 0. So this is what is given by this equation. So we subject the system to this input variation starting at 10 seconds, and up to 10 seconds the system behavior will be characterized by deviation of states, observer states, from the actual states of the system. And let us see how it happens. So this is what we see. Because Z1 is directly evaluated as X1, Z1 and X1 overlap to each other. However, because of the input variation that started at t equal to 10, the system faces a transient. So X1 varies in this fashion and again becomes constant somewhere little above 1.2. And Z1 follows that. Absolutely no error between X1 and Z1 because Z1 is equal to X1. That is the equation. We see what happens for X2 and Z2. Here, this is the plot of X2. So the systems, because that input variation starts at t equal to 10, the state X2 goes from 20 to something like 25 in this fashion. We see that this is the initial transient in Z2 because of the difference in initial condition. Z2, which was supposed to have been 20 if the system was, observer had also attained equilibrium, the state Z2 would have been 20. Then this initial portion of transient might not have been there. But in 10 seconds, it comes closer to X2, but not exactly X2. We saw it was requiring up to 25 seconds. But at 10 seconds itself, we have initiated a transient. So Z2, because it has to follow to X2 by design, so it starts following, but again, that happens only little later. But subsequently, you see Z2 is asymptotic to X2. Almost no error after some time. Same happens to the third state. This is how X3 varies because of that input variation that started at 10. And Z3 was already undergoing the transient so as to become asymptotic to this 20. But input appeared here and X3 started rising, so Z3 also started rising in its attempt to track X3 because the error has to be 0 after some time by design. So that happens. It approaches asymptotically. So what we have seen that if there is no input applied or if the input applied, the observer state in some time it starts matching to the actual system state. Z2, Z3, those two states, for that the observer was designed, reduced order observer was designed, and that design intent is fulfilled as seen for this example through simulations. We summarize the lecture. The reduced order observer devised by Leuenberger is of order n minus p. N is the system order and p is the number of independent outputs. In all other respects, it is similar to a full order observer. Means it is also a dynamical system. It is a feedback system. It takes the input and output of the actual system as feedback, as its input terminals, and its own state as feedback. So it is also a feedback system, and it estimates those all state variables. So those, of course, n minus p state variables of the system for which it is designed. It does that estimation. And again, we postulate, but we will show later in a subsequent lecture when we discuss the separation principle, that the state feedback control can be implemented using the estimated value of the state variables. This will happen. So with that, we come to end of this lecture. Thank you very much. See you again in another lecture.